Hi, my name is Shanaz. In last lecture, we see that the weak Hilbert's Nullstellensatz actually implies that the maximal ideals in the polynomial ring, say in n variables, are in one-to-one correspondence with the pointers P in the affine space An. So this is the weak form of Hilbert's Nullstellensatz, which says that the maximal ideals in the polynomial ring M are actually in one-to-one correspondence with the pointers P in the affine space. So this is one-to-one correspondence, and we proved in last lecture that if I is any ideal, I mean a proper ideal in the polynomial ring kx1 to xn, then the vanishing set of I is always non-empty. Now in this lecture we'll prove the Hilbert's strong Nullstellensatz. So actually it says that, so this is the Hilbert's strong Nullstellensatz. So it says that, so let J be an ideal in the polynomial ring in n variables. This is an ideal. Then the ideal of the vanishing set of the ideal J, actually it is equal to the radical of J. So by radical of J, so if A is a ring and I is an ideal in the ring A, then by radical of I we mean the ideal, I mean the set of all those elements in A whose I mean some power belongs to the ideal I, where R is some positive integer. So this is actually an ideal in A, and this is called the radical ideal of A. So, so this is called the radical of I. So we have proved, I mean the one direction, one uh, inclusion. I mean, so let us prove this. So we have proved that the ideal of the vanishing set of the ideal J actually contains the radical of J. So this is what we have done in previous lectures. So we now prove the other inclusion. So we now prove the other inclusion. So that is the ideal of the vanishing set of J is actually contained in the radical of J. So for this, let us pick some element, say F, in the ideal of the vanishing set of the ideal J. Now we prove this F is in the radical. So it suffices to prove some power of this element F is in the ideal J. Now one can note here the ring, I mean the field K is Noetherian. So is the polynomial ring K in n variables, I mean K x1 x through xn. So since the polynomial ring in n variables is Noetherian, so this would imply, so we can write J to be an ideal generated by finitely many elements of the ring, say f1 through fm, where these fi's, they are in the polynomial ring in n variables over the field k. So this is for I equal 1 2 up to n. So this follows from the fact that this polynomial ring is Noetherian. Now let us consider the polynomial ring. So consider the polynomial ring. Say over the field k, but in say n plus 1 variables. And let us define g, which is an element in the polynomial ring in n plus 1 variables, by, so we define this g to be a, which is a polynomial in n plus 1 variables, to be the polynomial 1 minus the variable xn plus 1 times the polynomial f, which is a polynomial in n variables. And let us suppose this so let us suppose L be the ideal generated by the elements f1 through fm and this polynomial g. So the ideal generated by the polynomials f1 through fm and the polynomial g. So of course this is an ideal in the polynomial ring in n plus 1 variables. So we claim that the vanishing set of L is empty. So we claim that the vanishing set of L is empty. So suppose not, it is not true. Suppose not, that let there be a point in the affine space. So let a1 through an plus 1 be a point in the zero set of the ideal L, where these ai's are in the field k, where ai belongs to k for all I between 1 and n plus 1. So one can note here, so if this is the case, that means each polynomial vanishes at this tuple. Now one can note here these polynomials, I mean the polynomials f1 through fm, they are the polynomials in n variables. So these polynomials they do not take this I mean this point an plus 1, because it is in n plus 1 dimension, because these fi's, they are the polynomials in n variables. So then fj of the point a1 through an, so this is 0 for all j equal to 1 through m, because we choose this point to be in the vanishing set of L. That means each polynomial I mean f1 through fm vanishes at this point, and so does the polynomial g. But if we substitute, I mean if we give this point uh, as an input to this polynomial g, let us see what would happen. And g of a1 to up to an plus 1, so by definition of g, this is 1 times, now xn plus 1 will assume the point value an plus 1, and f, it will assume the value a1 through an plus 1, sorry, an. Now one can note here this this expression over here is 0 because we choose f to be an element in the ideal of the vanishing set of j. So this is 0. So this gives 1, since the reason is that f belongs the f vanishes on the vanishing set of j. So since f vanishes at the vanishing set of the ideal j, but this is not possible because we choose this point here so that it is in the zero spot of L. So each polynomial, f1 through fm, they vanish at this point, but g does not vanish. So this means uh, mm, this set over here, this is empty. So this is not possible. Hence, the zero set of L, this is empty. Now we are going to invoke here the weak Nullstellensatz, because what we proved earlier, we proved that as long as I is a proper idle in the polynomial ring, it is zero set is always non-empty. But here we proved that the zero set of L is empty. So this is only possible if this ideal L is actually equal to the polynomial ring in n plus 1 variable. So by weak Hilbert Nullstellensatz, it follows that the ideal L is actually the whole polynomial ring in n plus 1 variables. So this would imply that the element 1 is in the L. So this further implies that 1 is in the ideal L, which is the ideal generated by f1 polynomials f1 through fm and polynomial g. So that means this one can be expressed as the linear combination of these elements. So this would imply, so that is there exists um, elements, the polynomial, say h naught, h1 through hm in the polynomial ring in n plus 1 variables, such that we can write this one as h naught times the polynomial, h naught, which is a polynomial in n plus 1 variables, times the polynomial g plus sigma, say I goes from 1 to m, hi of x1 through xn plus 1 times these polynomials fi, which are the polynomials in n variables, x1 through xn. Or this would imply 1 is h naught and g is the polynomial given by 1 minus xn plus 1 of f of x1 through xn plus 1 plus the sum I goes from 1 to n hi of x1 through xn plus 1 fi of x1 through xn. Now since f is non-zero in the polynomial ring K, so 1 over f will be an element in the quotient field of this polynomial ring. I mean the field of fractions of uh, the polynomial ring. So in other words, we can say 1 over f is a rational function. So since this f is non-zero in the polynomial ring with n variables, n plus 1 variables, this would imply 1 over f will be an element of k x1 through x plus 1. So by these round brackets we mean this is the field of fractions of the polynomial ring. So the field, the quotient field or field of fractions of the polynomial ring x plus n, n plus 1 variables, not n plus 1 variables, so this is n variables, so this is n here. So therefore the evaluation map, I mean if we send x plus 1 xn plus 1 to 1 over f, so this will induce the algebra homomorphism, k algebra homomorphism between the polynomial algebra kx1 through xn and the k algebra. So therefore the evaluation I mean if we send x plus 1 to the rational function 1 over f, so this evaluation will induce a homomorphism say from the field from the polynomial ring in n plus 1 variables to the field of quotient field x1 through xn. So this is what we get. So now under this map, this expression we can rewrite rephrase this expression over here. So under this map, the above expression which I underlined earlier, the above expression becomes I mean this expression over here. So we can rewrite this expression like this. So we have 1 is actually h naught, which is a polynomial in n plus 1 variables, and this n plus 1 now, so it becomes, so it is xn, and xn plus 1 becomes 1 over f times 1 minus xn plus 1 times f, that is 1 over f times f plus the rest sum, which is the sum um, of, I mean, the linear combination of these polynomials. So one can note here this becomes 0 because this is 0. So or 1 is actually equal sigma I goes from 1 to m h sub I of x1 through xn 1 over f. So this is fi x1 through xn. Now since each hi is a, so since each hi is a polynomial, so 1 over f appears with finite degree and finitely many times. So 1 over f appears with finite degree and finitely many times in this expression. So finitely many times in the expression star. Let's call this star. So that means we can take some power of f to I mean, so there exists some positive integer r such that f to the power r clears the denominator, clears the denominator. That is, so if we multiply by fr, so this will be a polynomial in just n variables, and this is again a polynomial in n variables, but these polynomials they are inside j. So that is f to the r will be actually sigma I goes from 1 to m f to the r of h sub I of x1 through xn and 1 over f. So this hi is actually a rational function. So when multiplying by f to the power r, so this denominator, uh, so there remains no denominator. I mean, we do not have f in the denominator. So this is f of x1 through xn. So one can see over here. So this f, this is in the so this is the, I mean, this right hand side is actually a linear combination of these fi's with coefficients in the polynomial ring in n variables. So this shows that this power fr is in actually in the ideal j, because this polynomial is in ideal j. So, so note that the right hand side is actually a linear combination of, this is actually fi's here, of fi's x1 through xn with coefficient in the polynomial ring x1 through xn. So this would imply this expression is in the ideal j. In other words, this f to the power r is in the ideal J. So this shows that f to the power r is in the ideal J, and hence f is in the radical of J as required. So this proves the strong Hilbert's Nullstellensatz. So what it actually says? So it actually says we have mutually inverse inclusion reversing bijections between the algebraic sets in the affine space an and the radical ideals in the polynomial ring in n variables. So let us make this uh, corollary. So we have uh, mutually I mean inverse inclusion reversing bijections between the set of algebraic sets in the affine space and the radical ideals in radical ideals in the polynomial ring in n variables. Now we call an ideal a radical ideal if I is actually equal to this radical. So from here to here we have the map I, and from here to here we have the map Z. So we know that both the maps are inclusion reversing mappings, and the map Z composite I is identity map, which we proved yesterday, I mean in the last lecture, and here by proving the strong Hilbert Nullstellensatz, we proved actually the I composite Z is actually the identity map on the radical ideals of I mean let us denote by Ri the set of radical ideals in the polynomial ring in n variables. Uh, so we have now here a short lemma which actually follows directly from the Hilbert basis theorem. So we have this theorem over here. So it says that every affine algebraic set say x in the affine space an uh, is actually the intersection of finitely many hypersurfaces is the intersection of finitely many hypersurfaces. So this proof directly follows from Hilbert-Basis theorem, which states that in a Noetherian ring, every ideal is finitely generated. So proof. So let X be an algebraic set in the affine n space. So then the ideal of X is uh, finitely generated. So this follows from the fact that the polynomial ring is actually, I mean, since so let us see So this is the ideal inside the polynomial ring in n variables is finitely generated. The reason is that this ring over here is Noetherian, since the polynomial ring is Noetherian. So this would imply, so this implies that the ideal of x is actually an ideal generated by finitely many polynomials. So where fi are in the polynomial ring for all 1 less or equal to I less or equal to n. So this would imply that the zero set of I of x is actually the zero set of the polynomials f1 through fn. So this is actually the zero set of f1 intersection zero set of f2 intersection so on zero set of fn. So since each ZFI is a hypersurface, so we are done. So this proves the result.